Imagine you're assembling a massive piece of furniture. You know the exact kind I'm talking about.
Oh, yeah. The ones with like 50 pages of dense instructions
Exactly. And hundreds of those tiny, identical screws.
and just that growing sense of dread.
Right. So picture this. Every single time the phone rings or, I don't know, the dog barks or the lights flicker while you're working, you are struck with total amnesia.
Oh, wow. That sounds terrible.
You literally drop your screwdriver, forget everything you've done over the past, 3 hours, and you have to start completely over from page one.
I mean, that sounds more like a psychological thriller than a weekend project.
It really does. But for you listening today, that scenario is, it's actually the reality for a huge portion of automated software processes out there right now.
Yeah, the ones we often call agents or digital workers.
Exactly. Because these systems, they can execute incredibly complex, multi-step tasks, right? Like they can draft reports, they analyze massive data sets, write code.
They do a lot of heavy lifting.
They do. But the second there's a minor network hiccup or a temporary server timeout or even just an unexpected data format, they just drop their tools.
Yeah, they forget their progress and start over from scratch.
Which if you're in an enterprise setting, that behavior is just so inefficient, it's frustrating, and it is wildly expensive.
Definitely. Which, that brings us to the source material we are pulling apart today for this deep dive.
Yes, it does.
We're looking at a highly specific developer implementation plan. It's for a system called Context Engineer Agentic Hardening.
Kind of a mouthful.
It is a dense title, I know, but the core mission is incredibly pragmatic. We are looking at how to take a notoriously fragile piece of software and fundamentally change its architecture.
Right, and our goal for this deep dive is to basically decode that developer blueprint.
Translate it, yeah.
Yeah, we're going to take this architecture and translate those core mechanisms into everyday concepts that make sense.
No AI jargon today.
None at all. We'll explore the data flow, the API modifications, and, the internal logic to see exactly how a system becomes completely crash-proof.
And budget aware, which is huge.
Oh, absolutely. And entirely resilient. We're talking about giving software firm boundaries, financial reflexes, and just a flawless memory, all without adding, like, an ounce of bloat to the code base.
Right. And the first major hurdle the developers had to clear was that amnesia problem you just described.
The dropping the screwdriver thing.
Exactly. Because to stop an automated system from starting over after every single interruption, it needs perfect recall.
Makes sense.
And the blueprint solves this through a pretty fundamental architectural shift. They implemented what they call a workflow state machine.
Okay, so I'm looking at the specific file they created for this in the sources. It's app/core/workflow_state.py.
Yeah, that's the one.
And the document says it wraps every single automated action into an, quote, idempotent, checkpointed step. Now, for anyone listening who doesn't spend their day staring at a code editor, idempotent is basically just a fancy way of saying that executing the exact same operation multiple times won't break anything.
Exactly.
Like it won't create duplicate results.
I like to think of it like an elevator button.
Oh, okay. How so?
Well, pressing it once sends a signal to call the elevator to your floor, right?
Yeah.
But if you're impatient and you mash that button 10 more times, you don't summon 10 elevators.
Oh, that's true.
And you don't break the panel, hopefully. The system just registers the intent and maintains that state.
Right. It knows you want to go down regardless of how many times you hit it.
Exactly. So in this software architecture, the workflow state machine applies that concept by constantly saving its progress.
Okay.
It writes every distinct step of its operation directly to a database. They specifically use Supabase for this.
Got it.
And it writes into two dedicated child tables called agent sessions and agent session artifacts.
Okay. And the blueprint also details this immutability trigger attached to those database tables.
Yes, that is a crucial part.
Because my understanding of an immutability trigger is that once a row of data like a save state is written into that table, the database physically rejects any subsequent attempt to alter it.
Right. No overwriting, no tampering.
It's permanently locked in. So mechanically, it's like a video game auto-saving right before a major boss fight.
Oh, that's a great analogy.
Right. Because if your console loses power during the battle, the system doesn't force you back to the very beginning of the whole game.
You'd probably throw the controller if it did.
I definitely would. But no, when you reboot, you spawn directly at that locked save point with all your inventory intact.
Right. So the system is persistently checkpointing its own reality. It refuses to move forward until the ground behind it is, completely solid.
I do have to challenge the efficiency of that, though.
Oh, how so?
Well, writing data to a remote database takes time. If I stop to write a highly detailed journal entry for every single step I take on a hike, my pace is going to slow to a crawl rate.
That is a very fair point.
And the document specifies that this workflow is broken down into a strict 6-state registry. So why limit it to exactly 6 states?
Right.
Why not checkpoint every single microfunction call just to be perfectly 100% safe?
Well, you nailed it with the hiking analogy. Saving every microsecond creates a massive performance bottleneck.
Okay.
So the 6-state limitation, it's a deliberate mechanism to balance that performance overhead with the need for catastrophic failure protection.
Got it. So it's a trade-off.
Exactly. The developers identified the 6 major boundaries of a task. These are the moments where the system shifts, say, from gathering data to processing data.
Oh, I see.
Or from processing data to formatting it.
So it only pauses to write in the journal at the major trailheads, basically.
That's a perfect way to put it. Let's apply this to a practical production scenario to make it concrete.
Okay, let's hear it.
Imagine a server crashes due to an unexpected power loss while an agent is right in the middle of generating a really dense, multi-page financial summary for a user.
Which normally would just be a disaster, everything lost.
Right. But because of the system event log, which is a component that emits highly structured tracking events strictly at those 6-state boundaries, the system isn't left guessing when the power comes back.
Oh, okay. So it knows exactly which of the 6 phases it had successfully completed before the blackout hit.
Precisely. So when the server comes back online, the state machine queries that agent sessions table.
The one in Supabase?
Yep. It retrieves that immutable record of where the run left off, and it literally skips the phases it already finished.
Really? Just skips them entirely?
Yeah, it logs a dedicated event for it, too. It's called step skip, and then it resumes the computation at the exact point of failure.
Wow.
It transforms what would normally be this catastrophic, resource-heavy failure into a minor, almost imperceptible pause in the workflow.
That is incredibly slick. So we've essentially built a system with perfect memory that just refuses to repeat its own past work.
Exactly.
But, stopping duplicate work internally doesn't really solve the external traffic problem.
Right. The outside world is messy.
Very messy.
Yeah.
If this system is actively saving its state, what happens when it gets rushed from the outside?
Ah, yes.
Right.
Stampede.
Right. Picture a user working on a notoriously slow Wi-Fi network. They click the generate button and nothing seems to happen right away.
We've all been there.
We have. So what do? They furiously click it 5 more times in a total panic.
Naturally.
Or even worse, what if an automated script goes rogue and tries to trigger the identical process 100 times a second? We need a way to prevent a total concurrency jam.
Yeah, you absolutely do. And that requires a really robust traffic control layer.
Okay.
The developers handle this in a dedicated service file. It's called workflow session service.py.
Right.
This service basically operates as a strategic choke point using what they term concurrency locks.
Okay, I want to dig into the actual mechanics of a concurrency lock, because the blueprint mentions it relies on a Asensio lock that is key to a specific session ID.
Yes.
So if I'm understanding this, every incoming request carries an ID ticket.
Correct.
If multiple requests hit the server at the exact same millisecond holding the identical ID ticket, how does the lock physically resolve that collision?
Okay, think of the Asensio lock less like a bouncer physically blocking a door and more like a strict take-a-number system at a really busy deli counter.
Oh, I like that.
It forces all those simultaneous requests to queue up in a single-file asynchronous line based on their exact arrival time.
Okay.
So request number 1 steps up to the counter and the system begins processing. But the really crucial part is how the system handles request number 2 when it finally steps up.
Because request number 2 is asking for the exact same sandwich that request number 1 is already having made.
Exactly. And the architecture follows a really rigid design principle here. It's explicitly laid out in the spec. The rule is generate equals start or check, never start again.
Never start again. Got it.
Right. So when the lock releases for request number 2, the service checks the active state of that specific session ID.
And it sees that the computation is already underway.
Yep. So instead of launching a parallel thread and doubling the load on the server, the lock simply catches the duplicate request, bundles up the current state of the running task, and hands it back.
Okay, I actually noticed the document specifies the HTTP response codes for this specific interaction.
Oh, yeah, the status codes are important here.
Yeah, it returns an HTTP 202 status.
Yeah.
And in web architecture, for anyone who isn't a web developer, a 202 status code translates to accepted.
Right.
It's basically a standardized way for a server to communicate, I've received your request, I'm actively processing it, please hold.
Yes, exactly.
And it responds to this immediately, which completely neutralizes the chaos of all that redundant processing.
The system pacifies those duplicate requests instantly. But there is a brilliant exception built into this logic, actually.
Oh, what's the exception?
Well, what if the original task has already reached 100% completion by the time that delayed duplicate request clears the lock?
Oh, like if the sandwich is already finished?
Right. In that case, the system bypasses the 202 accepted status entirely. It just returns a standard 200 OK status accompanied by the full completed artifact payload.
So, from the perspective of our frantic user with the terrible Wi-Fi,
Yeah.
their sixth desperate click just instantly delivers the finished report. They never even know they were queued up, and the server never had to run the heavy computation 6 times.
It perfectly protects the server infrastructure from basically unintentional denial of service attacks, and it totally isolates the user from the consequences of their own impatience.
That is so smart. Okay, so we have perfect memory, and we have an ironclad traffic control queue.
We do.
But resolving these technical hurdles kind of exposes a massive financial reality check, right?
Oh, yeah, the money part.
Because automated tasks are not free. Every time this software engages in complex logic, particularly if it's like querying external language models or processing massive data sets, it consumes tokens.
Yes.
And tokens act as a direct computational currency. Left unmonitored, a highly resilient system doing endless, perfectly queued work could literally bankrupt a department overnight.
Financial runaway is a severe risk in any agentic software. It happens all the time.
I bet.
But this implementation plan counters that risk by introducing something called the token budget guard.
Okay, token budget.
Yeah, you'll find it in app/core/token_budget.py. And if the Asensio lock manages the traffic queue, the token budget guard functions as an uncompromising financial auditor.
So it intercepts every single automated call and pre-flights the estimated cost against the user's specific subscription tier limits.
That's exactly what it does.
It operates identically to a prepaid debit card. Like, you cannot order a massive multi-course dinner if the card only holds enough funds for a basic appetizer.
Right, the transaction just declines.
The system physically checks the ledger balance before it authorizes the kitchen to even start cooking.
Yeah. The guard process calculates the projected token expenditure of the incoming operation. It verifies the user's tier allocation, and then it either greenlights the action or blocks it entirely.
Before a single fraction of a cent is spent.
Exactly.
Okay, but I'm looking at this specific line in the budget plan right now. It mentions a, quote, compaction threshold at 75%.
Ah, yes. The compaction threshold.
Yeah, that implies the system is treating 75% capacity like a warning track. Is it intentionally squeezing its own data footprint before it hits the ceiling so it doesn't just crash?
Yes, and that is the mechanical difference between a brittle system and a truly resilient one.
Okay, walk me through that.
Well, consider a user on a basic lower tier subscription, right?
Sure.
They upload a sprawling, incredibly dense library of reference documents, and they ask the agent to analyze the entire stack.
Which is going to be expensive.
Very. As the system ingests the data and begins processing, it is rapidly burning through its allocated tokens. Now, in a standard architecture, the moment it hits 100% of its budget, what happens?
It probably just crashes.
The process just throws an out-of-funds error, terminates the run, and returns nothing.
Oh, man. Which means the user burned their entire budget and received literally zero value in return.
Precisely. And that's a terrible user experience.
Also, is.
So to prevent that, the token budget guard continuously monitors the burn rate. The moment the session hits that 75% mark of its allowed budget, the guard proactively interrupts the standard flow.
Okay.
And it triggers a compaction routine.
Meaning what, exactly?
The system begins summarizing and compressing the older context it's currently holding in active memory. It systematically shrinks its own footprint to free up overhead.
Oh, wow.
Yeah, ensuring that the computation can actually finish and the user receives a completed, albeit slightly more condensed, final result.
So it's acting as its own pacemaker, basically. It's choosing to throttle its own fidelity rather than just outright failing.
Exactly.
That perfectly solves the storage side, but predicting computation costs in advance feels like an impossible physics problem.
It's notoriously difficult.
Right. How does the guard know how many tokens a complex, multi-step logical task will require before the task even begins?
Well, the blueprint is honest about this. It acknowledges that perfect prediction is essentially impossible.
Okay, so what do?
Instead of attempting to hardcode static costs, the developers rely on empirical data.
Oh, interesting.
The plan specifies they are launching the feature with, quote, placeholder estimates. But the critical mechanism here is a dedicated tracking metric called completion estimate drift.
Okay, completion estimate drift. So it's measuring the delta between the initial guess and the actual final invoice.
Exactly. Every time an operation concludes, the guard logs the predicted cost and compares it to the actual final token burn. And the document states that after 2 weeks of gathering real-world execution data from the top 90% of their active users, they will run an analysis on that drift metric, and then they will automatically recalibrate the budget thresholds based on statistical reality rather than just theoretical guesswork.
That is so cool. It's an architecture designed to observe and learn its own financial reality.
Yes, it adapts.
So we have the state machine handling the memory, we have the asynchronous locks managing the traffic queue, and we have the budget guard acting as the financial auditor.
We've got brilliant internal logic for sure.
We do. But, the true test of any software is how it integrates with the outside world. The plumbing required to expose these features has to be pretty extensive.
It is. The developers had to modify the core API routers to establish that connection.
Okay.
They introduced 4 new REST endpoints. This includes dedicated routes like generate skill package, and crucially, a GDPR-compliant delete route that permanently purges session history.
Oh, to adhere to privacy regulations. That makes sense.
Right. And additionally, they integrated 3 new MCP tools. That stands for Model Context Protocol tools.
Right, MCP.
These allow external AI agents to communicate securely with this system.
Now, the protocol integration is actually what caught my eye in the documents, specifically the XAPI key dual authentication requirement for those MCP tools.
Yeah, security is paramount there.
Because if external agents are going to be triggering these complex workflows, they absolutely need a secure handshake. The XAPI key acts as a mutual cryptographic verification, right?
Exactly.
It ensures that the system only accepts commands from authorized, verified external nodes.
It creates a highly secure, verified network of agents. But I think the most restrictive constraint governing all of this plumbing, the one that really defines the engineering philosophy of the entire blueprint, is their mandate of, quote, 0 new pip dependencies.
Oh yeah, I definitely want to talk about this. So for context for you listening, in Python development, pip packages are basically pre-written modules of code that developers download from the internet to handle specific tasks.
Right, they're like shortcuts.
Exactly. Need a tool to validate data. Download a package. Need a tool to format dates. Download a package.
It's how modern development works.
It is. So in modern software, building a massive architectural upgrade with 0 new dependencies, it's like deciding to construct a brand new wing on your house, but refusing to purchase a single piece of hardware or material.
Yeah, you're strictly limiting yourself to whatever tools and scrap wood are already sitting in your garage.
Right. So what is the mechanical benefit of forcing that kind of constraint? It sounds like a nightmare.
Well, in enterprise software, every single external dependency you introduce expands your threat surface.
Okay.
It's the mechanics of a supply chain vulnerability. If you download a third-party library to handle data validation and a malicious actor compromises that third-party library on the open web,
Oh, I see.
your entire hardened system is instantly compromised.
Because it's suddenly running their code.
Exactly. Furthermore, dependencies create version conflicts. An update to one package might inexplicably break another package.
Right, the classic dependency hell.
Yes. So by strictly confining themselves to the tools that are already vetted and listed in their existing requirements text file, the developers mathematically eliminate those risks.
Let's actually trace how they pull that off, because it's impressive.
Yeah.
They use FastAPI, which is already in their stack, to handle all the new REST routing.
Yep.
And for the state machine database, instead of installing some heavy new database driver, they just rely on PostgreSPI, which is a lightweight tool already present for communicating with Supabase.
Right. And to manage the token counting for the budget guard, they leveraged TickToken, which is an existing library they already had.
Okay.
For tracking the state machine phases, They utilize struct log to generate the system events.
Sure.
And that Essentio library we talked about, that's just part of the standard Python toolkit, providing those native queuing locks.
And the data verification is probably the perfect example of this. Instead of downloading a specialized, heavy third-party validation library to guarantee that the state machine saves haven't been corrupted, they literally just use Python's built-in hashlib.
It's so
It
elegant.
really is. It takes the output data, runs a cryptographic mathematical equation over it, and generates a unique string of characters, like a fingerprint.
Right.
If even a single text character in that database is altered, the fingerprint changes entirely, and the system instantly recognizes the corruption. All achieved using tools already sitting right there on the workbench.
And, that discipline extends to how they present the final output to the user, too. The blueprint dictates that all public API response schemas must be, quote, additive only.
Meaning the server responses will contain new data fields for the new features, but they will never alter, rename, or remove any of the legacy data fields.
Exactly. Consequently, any existing client software, mobile app, or external agent that's currently relying on this system requires absolutely zero code updates.
They just continue sending requests like normal.
Yeah, behind the scenes, the architecture upgrades completely seamlessly. The clients just suddenly experience a service that never drops a task, perfectly balances its budget, and handles traffic spikes without breaking a sweat.
Okay, let's pull all of these architectural threads together.
Let's do it.
We began by examining a fragile, automated process that was totally prone to amnesia at the slightest disruption.
The dropping of the screwdriver.
Right. But by engineering a persistent workflow state machine for infallible memory, implementing asynchronous queuing locks to organize chaotic traffic, establishing empirical token budgets for financial preservation, and executing the entire upgrade under a strict zero-dependency philosophy.
It's a lot when you list it out.
It is. But this blueprint literally transforms an unpredictable script into industrial-grade infrastructure. It is the literal definition of agentic hardening.
It absolutely is. It shifts the entire paradigm from software that requires constant human supervision to software that possesses the structural integrity to basically govern itself. But there is a final, really critical piece of the lifecycle we haven't touched on yet.
Oh, what's that?
How the system handles the massive accumulation of its own memory data. Because, the blueprint details a process, what they call lazy expiry.
Oh, I saw that. Because the state machine meticulously saves every single step, the database storage footprint could expand exponentially, right?
It would grow massive very quickly.
But they don't rely on centralized brute force deletion scripts to clean it up. They use retention windows intrinsically tied to the user's subscription tier.
Exactly. The data essentially expires naturally as part of the system's ambient operations.
Okay.
It's a decentralized approach to memory management. The system only retains the context it actually possesses the financial budget to store, and only for exactly as long as its tier allows.
That makes perfect sense.
And when we observe this architecture holistically, it prompts a deeply fascinating realization about the whole trajectory of automation.
Let's take that a step further, actually. What are the implications when we start chaining these systems together?
Right. If a single architecture possesses the internal mechanisms to perfectly pause its own processing, audit and budget its own computational currency, proactively compress its data to survive within strict limitations, and then eventually allow its own stored memories to expire based purely on mathematical tier limits,
It's kind of mind-blowing.
we are approaching a threshold. As developers begin chaining thousands of these hardened systems together, and they become increasingly adept at managing their own life cycles, their budgets, their memory retention, without any human intervention,
Yeah.
we really have to ask ourselves, are we merely engineering robust software tools, or are we laying the groundwork for autonomous digital organisms that fundamentally understand how to survive within their means?
There's a wild thought to end on. So the next time you drop your screwdriver and lose your place on page 50 of those furniture instructions, just remember, somewhere out there on a server, there is a hardened piece of software that knows exactly what step it was on, exactly how much the work cost, and exactly when it's time to just let go of the memory. Thank you for joining us on this deep dive.